Sunday event last Sunday where they talked about their book, Maths and Movies, to the normal Melbourne Writers' Week audience. And then, even more excitingly, they did much the same on Thursday when they met with a very large school audience and charmed a whole lot of young people. And even managed to prove that there are some young people who actually know some mathematics, because they asked questions they weren't expecting answers to, and they got answers. Some of them were even right. Marty has managed to excel himself by actually managing to mention the planet Mars on each and every occasion. So planet Mars has had a lot of mathematical airing this week, but it's going to get even richer right now. So please welcome one of Melbourne's math masters, Dr. Marty Ross, to talk about the maths of planet Mars.
Thank you very much for coming, and thanks tons for the MAV and Simon in particular, who's been our manager, roadie, promoter, and stuff for 11 years, and to come watch us 3 times in a week and see the same clips 3 times a week is above and beyond the call of duty. So this was the idea for this talk. Actually, I'll just give a very quick history of the idea of this talk. The title's actually due to Burckhardt, but it's not the first time I gave the talk. So just for those of you who haven't been with us for the last 95 years, or whatever it is, Burckhardt, these public lectures started in 2001. And the very first lectures I had was even before Simon. It was Sally Turnbull was the organizer at that stage, and she allowed me to give some public talks. And I try to come up with catchy titles. And the very first talk I gave, which surprisingly didn't get me into trouble, was The Joy of Gambling. I'm still astonished. I mean, Sally didn't know me from Adam. I'm still astonished that she allowed me to give this talk. Anyway, it didn't cause any controversy whatsoever. Though I figured, oh well, that was such a good title. Let's do it again. And last year, I had The Joy of Sports Gambling, which caused untold trouble, especially from this charming fellow on the left, who was a bit of a crusader and decided that I was devil incarnate. And thanks very much to the Simon and the MAV and the museum for fighting back. The point of the talk, of course, was not that sports gambling is joyful, but exactly what's going on with it. The irony seemed to be lost on me. Anyway, so I like these clever titles, but sometimes the titles can be too clever. And the second talk I gave in 2001 had the title, How and How Not to Contact Aliens. And I thought about this. I thought this was a really good idea. So you've got all these things about talking to aliens, some of them. And it's just how would you communicate with aliens? And specifically, what would be the mathematics of communicating with aliens? Of course, what happened was a whole bunch of people came to the talk expecting to be told how to communicate with aliens. And they were bitterly disappointed when I was talking about mathematics rather than sending signals and what had I heard recently. So you have to be very careful with the titles you choose. So now we've got this the same talk actually it's a similar talk, but it's the maths of planet Mars is again trying to think about how do we what's universal about mathematics, and how would we think about mathematics? How would Martians think about mathematics? And that's the purpose of the talk. I should say that the talks in 2001 didn't look like this. They were on very dusty transparencies. This was before Burckhardt came and semi-dragged me into the computer age. So anyway, the maths of planet Mars. So some of you may have come from the maths of planet Mars, the actual maths of planet Mars. This is all a play on the, I don't know how many of you have it. I don't think it's as prominent as some people may wish, though it's worldwide and quite big, is the mathematics of planet Earth, which is a international event or sequence of events trying to promote, well, the mathematics. Actually, it's more the mathematics for planet Earth rather than of one preposition is as good as another. It's just that basically, I would say it's all about global warming and climate change. Basically, is let's try to educate the public as much as anything else. If there are concerned scientists and mathematicians trying to figure out the way the planet works and what we can do to help it. Okay, so this is really, the mathematics to figure out the way the Earth works. And we're talking, the maths of planet Mars. Well, it's really what the maths is like. Actually, there's an article, it's all over the internet now. Is just a couple of days ago, life may have started on Mars, not Earth. So in fact, maybe the maths of planet Mars and the maths of planet Earth are exactly the same thing. Anybody see these reports? Yeah. Does everybody realize they're ridiculous? They're extremely speculative anyway. It's one of these things where you come up with a nice press release, kind of like a joy of sports gambling, but you're encouraging other people, is you come up with the right press release, everybody bites, even though there's very little substance to the actual reports. So don't expect the Martians any day soon. But if you're actually, that's right. So this is the maths of planet Earth, and Burckhardt actually thought of giving this talk. I think without knowing that I gave the How Not to Contact Aliens talk a long time ago. But he agreed to give it to me, and why should he give it to me? Well, of course, Marty, where's the name Marty and Martin come from? It's Mars, okay? So it's actually, it's got to be my talk, and actually the name comes from Mars, the god of war, which, for those who have been in some of my battles, is incredibly appropriate, but it's another story. Anyway, very quickly, the maths of planet Mars, here it is. 1/2, 1, 1.5, 2. There it is. Okay, just very quickly, the diameter is about half the diameter of Earth. The day is about the same as an Earth day. The distance is about 1.5 times the distance to the Sun, and the Mars year is about twice the Earth year. So now, if you're doing your NAPLAN science test, you plug those in and remember, and you'll be fine. Pretty much. Actually, the year's a bit off, about 1.8, but pretty good. Anyway, okay, but that's not what we want. What we want is how to talk to Martians. Okay, and this is movie week, the Melbourne Writers Festival. We showed lots of movies, but we talked about them too. Anyway, this is Devil Girl from Mars, which indicates there's easy ways to talk to Martians.
Who are you? My name is Naya. Where do you come from? Mars. Mars. Pathetic imposters. You men on Earth are much as we expected. We scientists were always skeptical about the possibility of life on Mars. Certainly nothing so human. You are a scientist? Yes. You are a very poor political president. Speak English. Of course. You are English, aren't you? What other language should I speak?
Okay, which sums up, about 90% of science fiction monster alien movies is they just speak English, all right, which makes things very easy. What other language would I speak? There's actually, this brings up, this woman here is Ma Ferguson, who's going down in history. She was governor of Texas about 100 years ago, Texas being the wonderful state that gave us George Bush and Rick Perry, and she was a fine precursor in that tradition. And if you know Texas at all, it's as much Mexican and Latin American as it is American. Right? And there's a huge Spanish-speaking population there, and bilingual education was an issue there. And Ma Ferguson typically was against it, and her supposed comment on it was, if English was good enough for Jesus, it's good enough for me. Unfortunately, she probably didn't say it, though it seems that there were people at the time who did say it, that they thought the King James Bible was kind of the Bible. And if it was good enough for Jesus, good enough for me. Okay, so if your Martians speak English, then you don't have any troubles. Okay? But what if they don't speak English? Well, okay, so we'll give it a go. So this is the man from Planet X.
Nothing works. He just keeps making that sound for everything we try to do. We've got to reach him. You have found a means of communication, Doctor?
Yes. What? Common denominator, Professor. The basic and universal language. Geometry.
By George, Doctor, you've hit it.
If anything should warrant success, this should. Excuse me, Professor. You've lost me. I'm the shadowy figure in the left background with a stupid expression on his face. I don't get this mathematics.
Well, there may be no scientific achievement without mathematics. In itself is the purest language of science. Now, this creature represents an obviously superior race of beings where science is concerned. To be able to land on the Earth from a planet whose existence was previously unsuspected.
Well, I'm up to you now. If there's anything our friend here should be able to understand, we might use as a bridge to reach him, it's this same basic language, geometry.
Precisely.
And we never actually figure out whether he understands. The movie actually turns into them kind of getting thuggish and beating up the guy, the aliens, so the universal language turns out to be violence, not mathematics. But you know, the idea is that geometry, what could possibly be common? We're going to talk to people out there, interesting Freudian slip. If we're going to talk to intelligent life out there, what basis could we use? And the idea is always that somehow mathematics ought to be at the basis, and they're talking about geometry here, and the question is which geometry? Okay, well, it depends on your aliens, of course, so if you happen to be attacked by a tetrahedra from space, that would be a good geometry to use. All right, so unfortunately the story doesn't live up to the picture, but it's a cool picture. Okay, so one person who would have loved it if we were visited by tetrahedra, and this is kind of where it started, is Johannes Kepler. So Kepler, so most of you would know Kepler, famous for? Kepler's laws, right, okay. Just like Marty's famous for Marty's laws. No, so Kepler, so he's famous for figuring out that the orbits of the planets were ellipses rather than these kind of circles and circles within circles, and two other laws of planetary motion. But where he started out was completely weird, is he asked how far, first of all, why there were only 6 planets? So what do we think of that question? Well, yes, well, that's one reason, is he thought there were 6 planets because that was kind of part of God's design, rather than, well, maybe if we looked a bit further, we'd see more. And why are they've got these certain radii of orbits, and where are they? How far are these planets from the sun, and why? What do we think of that question? Okay, so why is Mars 1.5 times the distance of Earth? Good answer. Excellent. Who said that? Excellent answer. Actually, it's debated. It's still debated now whether just because it is, you only got a few planets that got to get flung out one way or the other, but because it is probably the correct answer. Okay? But Kepler didn't think that. He thought again that this was all God's design. So he had this idea of putting tetrahedra and cubes and all these regular solids inside each other, and then the spheres which encase these things give you the orbits of the planets. It was all completely crazy. All right? So that was Kepler. The thing about it, though, so this is, well, it's not forgotten. It's just incredible. He's an incredible character. I mean, if you read some science history, reading about Kepler, he's one of the amazing stories in the history of astronomy, because he combined such intense mathematics with such craziness. So some of his ideas were completely crazy, and other ideas and other things were just brilliant. But one of the things was he He was around when Galileo peered through the telescope and saw the moons of Jupiter and the unevenness on the moon. And this convinced Kepler, not just Kepler, but certainly Kepler is one of the first, the trouble, of course, with Kepler looking through the telescope and looking at the moons of Jupiter is it kind of said, well, what's the big deal about Earth? If Jupiter has moons, then it's sort of suggesting, it doesn't prove, but it's suggesting that simply the Earth is just another planet. And the argument went, and this is Kepler wrote this to Galileo in response to Galileo's report of his findings, Kepler wrote, well, Kepler firmly believed that he thought that the moon was inhabited, and he firmly believed that Jupiter was inhabited. And the argument was, it's kind of a funny argument, right? In some sense, that's what we think now, right? We think, who thinks there's intelligent life out there? Who doesn't? Who thinks there's intelligent life here? Sure, that's right. We've got an election next week, and it's debatable. Okay, in some sense, that's, when there's all these kind of calculations of how likely it is that life would occur on a planet, things like that. But, the basic idea is there's simply nothing that special about Earth. And there's a hell of a lot of stars and a hell of a lot of planets. Why, why should it just occur here? But Kepler and other people who got onto the Copernican theory sort of pushed it further and said that because Earth wasn't a special planet, that guaranteed it. And again, it was kind of looking through the mind of God. He specifically said, well, Jupiter's got these moons, and until we had the telescope, we couldn't see them. So why are the moons there? So there have to be intelligent life on Jupiter to appreciate their moons. And he wrote this to Galileo. And Galileo's response to this question of whether there was life on other planets was basically, how the hell would I know? He just said, well, he wrote different things, but he basically was saying that I have no idea. I've got no scientific basis to decide one way or the other. Of course, this is very early on. It was like 1600, 1610. Even kind of the notions of air and gravity were not known. So he simply had no scientific basis to analyze the question and pretty much said so. And it kind of demonstrates that Galileo was a much, much better scientist than Kepler. Kepler was a much better mathematician, but Kepler had these flights of fantasy and was happy to go with it. But still, this was very common. There was certainly, whenever I prepare these talks, you sort of look for, you read in the background and stuff. I'm not an expert on SETI or anything like that, but you read the background. And the stuff on SETI will come to a bit, and the sort of the search transfer tracer and stuff was incredibly boring. It was really not good stuff. But the history of guys like Kepler and Galileo pondering this and the way they pondered and tried to figure it out was actually quite fascinating. It was great history. Anyway, that's trying, so the idea that there were, really that once the sun was at the center of the solar system, that really opened up the idea that there was intelligent life out there that we might say hello to. So how do we say hello to them? Well, the first person who seems to have had an idea of how to say hello to them was Carl Friedrich Gauss. It's not clear, actually, that Gauss was responsible for this, but all the suggestions go to it. So Carl Gauss was thinking, I think, it was a very prominent German mathematician and astronomer who was nameless, and it had to be Gauss pretty much. But the question was, if there's people or intelligent life on the moon, how could we signal them? Okay, this is early 1800s. This is before things like radio transmitters or anything like that. And his idea was to do this, put this diagram. So go into Siberia and cut down a whole bunch of trees and make this figure so that the moon people could see this figure. What's that figure? Pythagorean triangle, right? So that in the middle is a right angled triangle. So if you call it A, B, and C, then a right angle triangle, then a squared plus b squared equals c squared, which is actually, what it's saying is that the areas of the two smaller black squares is the area of the bigger black square. Okay? So, this is a way to indicate something intelligent to the moon people, that there's actually something, that we figured out Pythagoras' theorem. I mean, they call it something else, but the moon people would call it something else, but if they're intelligent enough, they could figure out Pythagoras' theorem. Well, no one went ahead with this, of course, but that was kind of the first idea to try to say hello to. Okay, things really got going in the 70s, and Carl Sagan and Frank Drake, if you know anything about this, they're kind of the big names in this attempt to contact aliens. And there's the Voyager spacecraft had that plaque labeled on it, and the Pioneer spacecrafts had this gold record with inscriptions on it, and then things encoded on the record as well, trying to get signals to outer space. Now, what are the odds that anybody's going to actually find these things? 0. I mean, it wasn't really about a concerted attempt to make contact with aliens. What it really was about was the message to ourselves that we're interested in the idea of contacting aliens. Okay? So they're just, you can draw pictures. If you send something out there, you can draw pictures, but the chances that anybody's going to find your spacecraft are minuscule. There's other interesting things about this. Oh well. Here's actually, it's amazing what some people do. They go frame by frame through movies and TV shows. I can't imagine such people. But actually, this was not one I found, but this is one that appeared in The Simpsons last year. So we've got an alien, and this appears for like about a second. And you got an alien holding the Voyager plaque. And you notice he's holding it upside down. Trying to figure it out. All right, here's a peeky in the brain. So the brain has changed it so that people, when the plaque is discovered, they'll realize he's the ruler of Earth. He's got Bibles down there, which is a nice thing to do. It's actually interesting, this thing about, it's so easy. One of the message about this is it's so easy to take things for granted, whether mathematical or just language or ideas. And this is, does anybody know what this creature is? It's not a Martian. Well, this was a creature discovered in the Burgess Shale, which is very famous for fossils from the Cambrian explosion because of very special circumstances, soft-bodied creatures were preserved. So there was a really rare chance. There's only like a couple of these places on the Earth. There's a really rare chance to see what soft-bodied creatures. Usually, all you get are the bones, right? You kind of try and piece things together, which is why you have debates. Well, did dinosaurs have feathers or whatever? Right? Because you simply don't have the full bodies. So this creature, which is so crazy, is called hallucinogenium because it was so crazy. And it was around, discovered about 100 years ago and kind of reinterpreted. I think the name hallucinogenium came around in the 70s, which is probably the era when you would call things such things. Anyway, but around 15 or 20 years ago, people reanalyzed it and realized that those kind of weird tentacly things up top, there was actually 2 rows of them, and actually it looks like that. So those spiky things were actually for protection up the top, and those tentacly things were actually things that walked on. So they actually had the whole animal upside down for 100 years before they figured out which way to put it. So, it's so easy. Why wouldn't an alien think, well, maybe it bounces around on that sphere thing, and then it's got these 4 available tentacle things to grab things. It's a good way to work. Very difficult to take. It's just so easy to take things for granted. Okay. All right. Now, this is if you're not going to put messages in a bottle. All right. So if you're actually going to send out things by radio signals and whatever, what do you send? Okay. And my apologies to Simon. Yet again, Simon. Simon has seen this clip so many times. Okay, but this is Red Planet Mars, and so what they're doing is they're getting signals from Mars which seem to indicate intelligence, and they're trying to figure out what to signal back. Okay? And all they can really do is kind of beep, beep, and dot, dot, and whatever. So they're trying to figure out what to send so that the Martians will realize that they're intelligent.
Well, this is no picnic you asked me on. You don't even know what language they speak, if any. It's like working out a system of communication with gollywogs. How the devil to find a point of contact?
How about pie? That's hardly the way to offer it, Stu. And by the size of that slice, I doubt if there's anything left.
I mean pie.
Now, what are you talking about?
Well, if we're getting answers, they have to have a transmitter as powerful as ours.
Go on, what are you driving at?
Well, they can't build anything like that unless they know how to make a wheel. That means a circle.
And you can't make a circle without knowing the ratio of the diameter to the circumference. Pi. I still don't understand what that has to do with your son's ahead of your chroma. What is pi?
3.1416, as I remember.
Roughly. That's it, roughly. Actually, it's 3.1415926 and so on, an infinite number of decimals. Well, so what? We broadcast 3.1416 to Mars, and what can they answer? Nothing. But they must be trying as hard to talk to you as you're straining to talk to them. All we're looking for is an opening. So, you don't broadcast 31416. You broadcast 31415. And if they understand, they continue the equation, right? Where'd you get that idea, son?
Biting into this.
Okay, all right, so the idea is, you know, an intelligent civilization, at least an intelligent enough one to send us signals, ought to know about pi. So, you know, you send digits however many you feel like sending. So they're just sending a few, then the idea is send a few and then get them back. What's wrong with this? Base 10. Yeah. So here we have a three-legged Martian, and he's saying, well, maybe they'll send me pi. And so what he's hoping to get is those. Okay. So he's getting all these digits, and he's trying to figure out, what is that? Now, 3, 1, 4, 1, 5, what on earth is that? Right? Now, if I told you, if I sent you the digits 1, 0, 0, 1, 0, 2, 1, 1, 0, 1, would you be able to figure it out? Take long? Maybe not. You might guess, but it's certainly not natural. Okay. So the whole thing about it, right, is 3 times 1 plus 1/10 plus 400 plus 1,000 and so on. But you can do that, you know, not decimals, but what do you call them? Triasimals. So rather than you have 1 times 3 plus no 1s plus no 3rds plus 1/9, 27ths, 81st, and so on. Okay. So you know, it's a good idea, but you know, it's. Yeah, if they're intelligent enough, they'll probably figure it out. But it's certainly, the whole thing is why do you use base 10? 10 fingers, okay? So just assuming base 10 is certainly, it's the kind of mistake you can make. Just for practice, we're gonna do a bit of this later. What is 2 times 2 in base 3 for the Martian?
11.
Yeah, you probably it's better to say 1, 1 rather than 11. It's kind of weird with these names, is what counts as a base 10 thingy and what doesn't. That's right, it should be 1, 1. 2 times 2 is 1, 1. Okay, so any kind of arithmetic you do with base 10, the Martian can do just as well, but it would look very different if you start sending signals. Okay, all right. So, you got to do better than that. So, very famous movie based on a very famous novel. Actually, it was supposed to be a movie before it was a novel, but the movie took about 20 years to get going. So he turned it into a novel first. So this is Jodie Foster trying to figure out the symbols.
All right, it's restarting. Wait a minute, those are numbers. That was a 3. The one before it was a 2. Base 10 numbers, just start counting now, see how low we can get. 1. 7. 2 times 2, 3, 5, 5, 7, those are all prime numbers. And there's no way it's a natural phenomenon. Okay, let's just calm down and...
Okay, very famous scenes. All right, so they're getting these signals, and it's certainly a great idea in how to indicate something which has got a pattern but doesn't have a pattern, right? You don't want to indicate that something has got a pattern because then it could just be natural, all right? But you need to indicate something, and the prime numbers is a beautiful way. They're just kind of, mathematically, it's just what comes next is kind of what comes next. It's kind of sort of like the orbits of the planets. In some sense, it's almost as not understood as much as why the planets are where they are. They just are. Right? 2, 3, 5, 7, then you got a step, then 11 and 13, got a step, 17, 19, got a step, 23, got a step, and so on. They did, it's subtle, but what was wrong with the scene? Very subtle thing. But it's the kind of thing which really annoys you if you're a mathematician, especially a mathematician collecting maths and movies. Yeah. Well, she referred to base 10 numbers, which actually makes no sense. There's no such thing as a base 10 number. Numbers are numbers. Okay. All right. So it didn't. I mean, it's certainly primes are just they're primes are primes are primes. Okay. So it's exactly getting away. I mean, the whole point of primes is you don't need the base in order to interpret them. Okay. Question is now what? Okay. So there you got intelligent life. What do you do with it? Well, the simplest. So you can indicate something intelligent. So here's seeing, this is not an alien movie, though it's a pretty alien movie, pretty weird movie. So Fermat's room, and this crazy man's locked these people in a room and giving them puzzles to solve, otherwise the room's going to close in on them. So, high-stake test, as they say.
Tenéis un minuto para descifrar el siguiente código. 1, 1, 1.
¿Cómo es el código?
Es una lista enorme de unos y ceros.
1, 0, 1. ¿Cuántos números son?
Sí, estoy contando 167, 3. Son 169.
¿Sabéis lo que es 169, no? Tengo una idea, necesito algo, trozos de alguna cosa. Su hija, lo tengo. 169 tenía que ser 13 por 13, las coordenadas de un cuadrado. Los unos y los ceros forman el dibujo de una cara, ¿veis? 0, 1, 1, 0, 0, 0. Por lo tanto, solución...
Es que no es una cara. Es una calavera.
Okay, all right. So I've got 169 zeros and ones, and you arrange it into 13 times 13, and you end up with this skull, and that's the answer, and then the room doesn't close for a moment. All right. And this is exactly the idea, well, not from the movie, but Arecibo, this is exactly the way that the Arecibo message, which was basically a bunch of zeros and ones sent out. There they are. Okay, everybody figured out what that means? Okay, right. Well, you got a while, right? So the same thing is you repeat this. It's about 3 minutes long, and you keep repeating it. And it turns out there's 1,679 digits there. And what's special about 1,679 is 23 times 73. So it's a product of 2 prime numbers. Okay? And the idea is these people are going to ask why these people, that was so easy to say that, these intelligent beings, all right, so people centric, these intelligent beings are going to figure out, 23 times 73, 679, factorize that, 23 times 73, why that? Well, we can arrange that, then you can arrange the zeros and ones into a grid, all right, so it's just either on or off. And if you do that, don't worry about the colors here, but if you do that, you get this. Well, that makes a hell of a lot of sense. All right? Colors actually do Wikipedia, which has got a beautiful page on this. All right, but it turns out 1,679 is also 73 times 23. And if you arrange it in the other way, then you get the intended message, which is that. Okay. So why didn't they, in Fermat's room, they had 169, which is 13 times 13. Why didn't they do something like 23 times 23, or 73 times 73? Beg your pardon? Well, 23 times 23 is smaller. So you could choose the prime numbers, to be whatever size you want. You could, it'd be a square rather than a long thin thing. writer says, I mean, it's a lot of this. I mean, this kind of idea, it actually was before the Arecibo message. People had this idea of sending zeros and ones as a product of two primes, and then people could unravel it as in this shape. I think the idea is that if you send something like 23 times 23, it's indicating that the number 23 is special. So the thing, if you're trying to not, you're trying to send a clue of what matters, but then you're trying to send a clue of what, you're not trying to send false clues. So 23 times 23 is somehow saying 23 is an important number for us. Of course, you could use an important number and then whack up. So, do we make sense? Can we make sense of this message? The colors, again, that are not broadcast, but this is very nicely done in the Wikipedia page to kind of indicate the separate parts of the message. Has anybody gone through the interpretation of this, or can you see anything which actually makes some sense?
One point that looks like a closer than it is.
Yeah, so some person, the red thing is meant to represent a person.
Spaceman at the bottom.
Yeah, the purple thing at the bottom is supposed to indicate the parabolic telescope thing up. Anything else?
The line at the top is, I think it could be binary.
Who said that? Excellent. Excellent. It's not easy to see. I mean, the other thing is, of course, these things might be upside down and whatever. But we'll get to that in a second. Does the yellow thing mean anything? Yeah, the answer is yes, it does, but does it mean anything to you? Might mean anything to an alien. It might not. It's supposed to be the solar system. So the 3 by 3 yellow square is supposed to be the sun, then you've got one little planet, second little planet, third little planet, which is offset to indicate that the red guys come from that, fourth little planet, fifth big planet, sixth big planet, seventh medium planet, eighth medium planet, ninth Pluto. Okay? So it's a combination of sort of trying to do pictures, but then, that's right, this thing up the top, if you ignore that bottom line, which is trying to indicate what's going on, and write it out, and think of it as ones and zeros, you're getting 1, 0, 0, 0, 1, 0, 1, 0. You're getting the numbers from 1 to 10 in binary. Could aliens figure this out? You know, one thing to keep in mind, of course, is, you know, where you're here on a Sunday morning, you may have had a few glasses of wine last night, and then you're trying to figure out a message that someone's throwing at you. It may take you a while. But if you're getting this kind of message from space, you're going to be working mighty hard to figure it out. So the fact that it might not be figure-outable in half an hour or an hour, that you might take you out days or weeks or months or years to figure it out, doesn't mean that it can't be figured out. So the whole idea is to try and make it decipherable as possible. Can it be figured out? One of the things is it's clearly a weird combination of mathematics hidden in the message together with pictures, using the zeros and ones. This was taken to hilarious extremes by this guy, Hans Freudenthal. Has anybody heard of this guy? He's very famous for 3 reasons. One to do with this kind of SETI research. He's also he wasn't famous as a mathematician, but he was a very good mathematician. I mean, needless to say, there's lots of really good mathematicians that no one ever hears of. So he did a lot of work in what's called topology and was a very accomplished mathematician. He's famous, he's probably most famous now for what's called the Freudenthal Institute, which is a Dutch maths education institute, which apparently does a lot of work, and there's a lot of controversy over it at the moment. He's also famous for something called the impossible puzzle, which this is just a bit of a detour, but it's kind of too good a detour not to go on. So Freudenthal came up with this puzzle, all right? So the puzzle involves, you have to figure out the puzzle is to try to figure out 2 numbers. So there's 2 numbers that you gotta get. The numbers are bigger than 1 and less than 100, and they're different. Okay, and this is the information you have. Okay, I'm going to give you the information you have to try to figure out these numbers. Okay, to do this, I need a volunteer from the audience. You in the back? Okay, all right. Sir, have we ever met before?
Never.
Okay. All right. Do you want to begin?
Okay, I know the product.
I know the sum.
I don't know the numbers.
I don't know the numbers.
Oh, I know the numbers, no.
I know the numbers. That's it. Assuming we're telling the truth, figure out what the two numbers are. It's a great puzzle. I'll let you ponder that. So he came up with this puzzle. All right, and it's really a brilliant puzzle. There's different versions of it. It was called The Impossible Puzzle by Martin Gardner, who wrote about it. And if you say it slightly different ways, it either mucks up the puzzle or you get different answers. But anyway, I'll let you think about it. He's very famous for that Impossible Puzzle. He's also famous for a book called Linkos, which is short for Lingua Cosmica. Language of the cosmos is how do we talk to aliens. All right, and so what do you do? So he starts out, this is kind of the indication of he's going to explain, first of all, and you're just doing like bips, 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 he'll explain that there's a special sign, which we write as bigger than, there's a special sign which we write as less than, there's a special sign which we call equal, so you're going to have a whole bunch of blips to explain, these are signs, I'm going to use these signs. Then you have to say what those signs mean. So this is where it starts. So for instance, dot, 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 dot is bigger than dot, dot, dot. That's explaining, that's an example telling the aliens that arrowy sign indicates bigger than. The and so on means you're going to give a lot of examples of this. So you might give an example, 11 is bigger than 6, or 12 is bigger than 5. Do a few examples of that, and then they know what bigger than is, and then they know what less than or equal to is, and then they know what equals is, and so on. And slowly, 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 you build up, and then about 150 pages later, there he's got the sketch of the history of Fermat's theorem. It goes on describing the planets in the solar system forever. It's hilarious. It's just a hilarious book. It's designed as, it's exactly the exact opposite problem of codes, right? When you're doing a code, you're trying to make things as hard as possible for anybody to decipher. This is trying to build up tediously, slowly, but carefully, so that you can understand it. And it's just remarkable. Does it work?
September 2nd, 10 p.m. Leon Van Heusen, single, ambitious, slightly paranoid. By day, a television repairman. By night, an observer, a man with a purpose. The author of Mathematico, a universal language that Leon has refined for use in unconventional communication.
Your present location is the third planet of our star system. We are peaceful. I will now address you in Mathematico, the universal language.
You have to try it on the right kind of alien. So, anyway, okay. Needless to say, no one's actually implemented this, but does anybody here actually read the SETI stuff and the kind of? It's remarkable. Some of the stuff. It's remarkably boring, as I say. These people are so trying hard to figure out how to send intelligent messages, and it's so weird and so complicated what they're doing. And it makes some kind of logical sense, right? That you build up these things from this language, but it's in some sense it's just for the hell of it. Let's go a little slower. So rather than explaining Fermat's last theorem, let's just see what we can get. I love this book. I don't know, has anybody read this, Martian Odyssey? It's Stanley Weibbaum. The story was written in 1934, and then he died in 1935. It's an amazing story. This is where it appeared. Unfortunately, the cover has a picture of a different one rather than Martian Odyssey. But it's a great story. You can find it for free on the internet. I just love it. It appeared. Anybody know this? Science Fiction Hall of Fame is probably the greatest collection of science fiction stories ever. It's just an amazing collection of stories collected in the 70s, and it was voted on by the science fiction writers as what they regarded as the best stories of the century, or before 1964, I think. And they're just, almost all of them are brilliant stories. lots of deeper meaning and things like that. The number one story by quite a long way was a story called Nightfall by Isaac Asimov, which is very famous, which I didn't think was that good. But the number two story was A Martian Odyssey, which was not at all a kind of deeper meaning thing. It was simply this astronaut having an adventure on Mars. He gets stranded on Mars, gets befriended by this strange ostrich creature called Tweel. That's the kind of sound it makes, so he calls it Tweel. And they try to communicate. And the way they try to communicate is just, there's something really wonderful in the story. So he's reporting back up and says, after a while I gave up the language business and tried mathematics. I scratched 2 + 2 = 4 on the ground and demonstrated it with pebbles. Again, Tweel caught the idea and informed me that 3 + 3 = 6. Okay? And then, so that was their first kind of communication. And the thing I love about it is it's a great, you get the real sense. It's a great story. You get real sense that Tweel is this intelligent creature without having any sense of how it thinks. But there's this little connection in mathematics. And later, they're talking, and they come across this one weird Martian monster, and Tweel says, no 1, 1, 2, no 2, 2, 4. And later they come across a creature, another creature, and Tweel says, 1, 1, 2, yes, 2, 2, 4, no. Okay? So it's trying to get some sense, trying to say something with the very minimum of language, the notion of yes and no, just the notion of 1 + 1 = 2, and 2 + 2 = 4. Okay, well, let's slow down. 1 + 1 = 2. 2 + 2 = 4. Why? How do you know 1 + 1 = 2? Excellent. Yes. Because that's what it means. 2 means 1 + 1. Right? You add 1, you move 1 step along, we give it a new name, and that's 2. Why is 2 + 2 = 4? What does 4 mean? Yeah?
1 + 1 + 1 + 1.
Excellent. Okay, so 1 + 1 is 2, then +1 is 3, and then +1 again would be 4. So 4 is actually 3 + 1. That's what 4 means. So why is 2 + 2 = 4? Yeah?
Because you can move it differently.
How do you make it work differently? Excellent.
1 + 1 goes with it plus, but we make it 1 + 1 goes with it.
Excellent. Excellent. Okay? The thing is, you have to figure out what +2 means. +2 means to add 1 and then add 1 again. So 2 + 2 actually means first add 1 and then add another 1. But 2 + 1 is shorthand, that's 3 + 1, and then 4 is what we mean by 3 + 1. It's actually, the point is, yeah, 2 + 2 is got to equal 4, but it's actually more, it's kind of subtle. There's something going on. There's a real mathematical leap just going from 1 + 1 = 2 to 2 + 2 = 4. So I'm just assuming how much mathematics you could, how intelligent do you need to be to know 1 + 1 = 2? To have the notion of adding, or the notion of stepping on. But then actually to get some notion of adding is hard. Actually, Hans Freudenthal, and he's a very bright guy, and he talked about what he was doing with Limkos. And I think for him, largely, he wasn't really interested, the book was written in 1960, he wasn't really interested in contacting aliens, he was interested in the logical exercise. But he wrote about it this way, he said, I shall suppose that the person who is to receive my messages is human, or at least human-like as to his mental state and experiences. I should not know how to communicate with an individual who does not fulfill these requirements. He was simply saying, if they don't understand such things, and we can't get it through this way, I'm lost. What do you do? If you can't imagine it, you can't imagine it, in a sense. But this is kind of the only thing that works. Okay, now, this is my favorite puzzle. It's a bit chucked in, but it's actually, there's a point to it. So I'll just say the puzzle and then connect it back. So Bear leaves his home, then he walks 20 kilometers south, then 20 kilometers east, then 20 kilometers north. He discovers that he is home. The question is, what color is the bear? Yes? He's white. Why is he white? He's a polar bear. Why is he a polar bear?
He started
At the North Pole. Excellent. Okay, it's a wonderful puzzle. Okay, so we'll go through it in a second. There's actually a better answer. So the answer is white. Actually, a better answer. Lots of people who know the puzzle don't actually understand. So the better answer is the bear is penguin. So this is what you got. Okay, so this is 20 kilometers, not going to do, but you can imagine a big triangle. So you go south, then east, then north, and you actually end up back where you started. Okay? So somehow right angle things. So why is he? So that's the standard solution. Why a penguin? So I didn't get another graphic here, but you can't start at the South Pole because if you start at the South Pole, then you can't go south. But you start just a little north of the South Pole, so 20 kilometers takes you very close to the South Pole. 20 kilometers east takes you a full lap around, and 20 kilometers north takes you back up. So there's actually other solutions as well, not just the North Pole. It's a wonderful puzzle. It's really a wonderful puzzle. The point here, as I want to point out, is those are right angles. So we got a right angle triangle. Talk about whether it's really a right angle triangle. All right. Actually, there's two right angles. That's kind of a big weird triangle with two right angles. Is a squared plus b squared equal to c squared for this triangle? Definitely not. Okay? So now that has is that really is that a fair triangle? Why not? It's not flat. Is it really not flat? Some of it's curved, some of it isn't. The lines of longitude are not curved. The lines of longitude are as straight as they can be. The circle of latitude, so the going east bit is cheating. But the lines of longitude, they are as straight as can be, staying on the Earth, just like the equator.
I dispute that. There's actually a particular view of the axis through North Pole, South Pole. If you turn to a diagram on its side or around.
Well, then you would have different longitudes. So at any point, you could imagine any point as being the pole and doing longitudes down from that. So yeah, the North Pole just happens to be the North Pole because that's kind of like a cold point with magnets and stuff like that. But any point you can put in your coordinates so that the lines going down, like the equator. The equator is as straight as possible. The shortest distance, if you go along the equator, as long as you go in the right direction, that would be the shortest path between 2 points. You have 2 points on the equator, you want to get there as quickly as possible, the shortest path is along the equator. Okay?
It's a sphere though.
Yeah, but it's as short as you can do. Okay? Now you can make this, if you actually made this triangle go down to the equator, you would actually be fully correct. What about this circle? This is a circle on the surface of the Earth. Is the area equal to pi r squared? No. And you wouldn't expect it to be. Okay? But the thing is, you can do exactly the same thing in space. Okay, so this is Bernhard Riemann. Gauss had the idea that you could capture the notion of how curved surfaces like the Earth are. And Bernhard Riemann had the notion that three-dimensional worlds, our world, can be curved in exactly the same way. So that the area is not actually equal to pi r squared. The area, if you look a little circle, is equal to pi r squared minus the curvature divided by 12 pi r to the 4th power. So the fact that space is curved, you have some notion that space is curved. Space can be curved exactly the way the Earth is curved. Not because it's curved in something else, but it's curved in its very nature. Okay, which is getting pretty weird, but one thing it's saying is, well, is pi equal to pi? If Martians get the areas of their circles, would they get pi r squared? Well, actually, they get pretty close, so it's kind of a moot point, just like we do. But anyway, it's not quite there. And Pythagoras' theorem is not quite a theorem. These are theorems about ideal mathematics. They're not actually theorems of our physical world. Our physical world is different. Which you're probably trying to think, well, Marty really has gone into space. I just have a quote. There's a student from ANU who just finished his honors thesis in this kind of stuff and in differential equations. He emailed me for some advice on some things. And he just randomly wrote about a month ago about the difficult maths he was hoping to accomplish. And he said, oops, built the wrong way. I'll let him finish. Research, particularly those long proofs leading to some regular result that ordinary people would consider it from Mars. So the maths that we do is so weird that it may as well be from Mars. Okay, just quickly, what could the Martians teach us? Okay.
Every new weapon invented, a defense is perfected, until the ultimate weapon was developed, a perpetual motion chain reactor beam. What form did it take? As fast as matter was created, it was changed by its molecular structure into the next dimension, and so destroyed itself. So there is a fourth dimension.
Okay, well, they can teach us that. But they can teach us something else. So this is actually, I like this. I mean, one of the things is maths is, the idea is what maths is universal and what's kind of special to base 3 and base 10. And if you do things like 1 times 1 is 1, 2 times 2 is 1, 1, it looks different. But it's actually something, if you're lucky, you can actually learn something just because you happen to look at math the right way. So what's 1, 0 times 1, 0? 1, 0, 0. What's 1, 1 times 1, 1? If we're lucky, it's 1, 2, 1. Is it? So if we translate it into base 10, it actually works out. So it's 4 times 4, which is 16, which is 9 plus 6 plus 1. So it's actually 1, 2, 1. What's 1, 2 times 1, 2? Yes. No pens. Okay, so now it's getting complicated. But of course, you can do exactly like you do in normal arithmetic. So first you're going to do 2 times 1, 2. That's 1, carry the 1, and then you get 1, 0, 1. Then you do 1 times 1, 2. Move in place, add it up. All right? Just exactly as you would. You don't have to translate things into our base 10 thing, do the multiplication, and then translate back. You can simply do it. So that's that. 2, 0 times 2, 0. That's actually an easy one. Well, 2 times 2 is 1, 1. But you got a couple of zeros there, so it's got to be 1, 1, 0, 0. Okay? The thing about these are all square numbers. The thing about it is, squares always end in a 1. I mean, there might be some zeros, but the rightmost number is a 1, not counting the zeros. Will be whoop-de-doo. Right? So 1, 0 times 1, 0, you've got ignore the zeros, you end in a 1. 1, 1 times 1, 1, you end in a 1. The rightmost number is a 1, and so on. Who cares? Can you look at the equation a squared equals 2b squared? So can you get a number, square it, another number, square it, and the first number is twice the second number? No, why not? Beg your pardon?
They all end in 1, 2,
The left number must end in a 1. What's the right number ending? Well, the b squared ends in a 1, but then you multiply by 2, it's just going to end in a 2. Beg your pardon? It's base 3, so the last digit doesn't tell you where it's thing, but it's just looking at the last digit. The last digit of the left-hand side is a 1, the last digit of the right-hand side is a 2. It's impossible. So what? What's special about that equation? It tells you that root 2 is irrational. There's no, if you divide both sides by b squared, it's telling you that there's no fraction whose square is equal to 2. Which is kind of, we just wrote about this, and it's kind of notoriously difficult to try to get this idea across. But for Martians, it turns out it's actually really easy. Okay, so maybe they can teach us a bit just because of the peculiarity of it in mathematics. And that's a very good place to end. Okay, thank you very much.
Well, the 15th of September is the next one, and the last for 2013, except that we will be having a series of presentations from Martin Burkhardt and some school excursions in November at Fed Square, so that's something worth looking out for. But on the 15th, we'll be talking about